All right, we're getting into now one of the most important concepts of linear algebra, and that is linear combinations and then translating that into spans. So a linear combination is very similar to what we did at the beginning of this chapter, where we're going to be solving a matrix. But the definition is that there is a vector, y, that is equal to a constant times each and every input on the vectors v1, v2, vp. So you've done this potentially before when we've done like a system of equations, right? But now we're going to go into more dimensions, and we want to figure out like what is it? What combination, if it exists, of C1 different scalars, all these C scalars, can we get to be this vector in the front? I think it's best shown with an example here. Okay. So I have A that's in R3, A1 that's in R3, A2 is in R3, and B is in R3. Determine if B can be generated or written as a linear combination. If you just see those words, I copied this from the text, the full thing, but if you see, can this be written as a linear combination, that's what this next part, this is what it means. That is, can you find x1 and x2 where this is true? So I want us to solve this just like we did solving systems before. We're going to set this up, okay, with my A matrix, A1 column, my A2 column, and then I'm going to augment that with my B column. And I'm going to try to find an x1 and an x2 for which this is a true matrix, okay, for which it has a solution. All right, so the first thing I'm going to do is I'm going to look at 2 times R1. I'm going to add that to R2 and put that back into R2. And I'm going to take 5 times R1. I'm going to add that to R3 and put that into R3. So row 1 stays the same. Row 2, I get 0. 2 times 2, 4, plus 5, 9. 2 times 7, 14, plus 4, 18. 5 there gets canceled. 10 plus 6, I get 16. 35 minus 3, I get 32. All right, so notice here, I can multiply R1 and R3 by, or excuse me, R2 and R3 by a half. If I do that, I get 1 and 2, and again, I get 1 and 2. Well, those are the same. So really, I can just replace this last row with zeros. Or you can say negative R2 plus R3 back into R3, and those are just going to cancel out. So what does that give me? What that gives me is that 1 times x2 must be equal to 2, or x2 must be 2, right? Or if I just look at that solution here. You could go back to reduced row echelon form, or we can just go ahead and plug in 1 x1 plus 2 times 2 must give me 7, which means x1 must be 3. We can then check this, okay? So yes, if it has a solution, we have a linear combination. We've figured out the weights, as they are called in our text, of x1 and x2, in which this is true. And you can go through and you can check back up here. Is 3, because that's my x1 weight, times 1 plus 2 times 2 equal to 7. Well, I would hope so. That's what we just solved, right? Is 3 times negative 2, looking here, plus 2 times 5 equal to 4. That is true. Is 3 times negative 5 plus 2 times 6 equal to negative 3? Also true. So this is a linear combination, and those are the two weights. x1 equals 3, x2 equals 2. That brings us into a linear equation. So a linear equation, just like the one we looked at, can be augmented as a matrix. That's how we solved it, if and only if there exists a solution to the linear system, okay? Now, the other thing that we say is that if you have a collection of vectors, we want to talk about the span. The span is the collection of all vectors, all linear combinations, if you will, of this space. And I personally think the graph down here helps us understand the most. So you take essentially a span and a linear combination are very, very similar. You take a linear combination, you take multiples of C1, so on and so forth, okay? And you are going to take those multiples. So it's going to take that vector and span it out. And so if you end up having that full span in R2, you would have that full line, okay? A full span in R3, this is in R3, is, well, U needs to go in this direction, in this one, right? V needs to go here and here, and then they said that your next one is U plus V, so that needs to go here and here. So you have that plane, okay? And so we say a vector is going to lie in that span if it's on this plane, or if it's within that linear combination of all of those vectors. All right, so let's look at this one. We have A1, A2, and a B. Span A1 and A2 is a plane through the origin of R3. Well, that makes sense because I have an X1, an X2, and X3. These are here, okay? Is B in that plane? Well, let's go ahead and check. If it is, what that means is, if we go back to that definition, X1, A1 plus X2, A2 would give me vector B. Okay, it would be a combination, a linear combination of those if it's in the span. So we're going to solve this just like we did on the other example. And see if this is true. All right, I'm going to take 2R1, add to R2 and put that back into R2. I'm going to take negative 3R1 and add R3 and put that back into R3. I get zeros when I do that here. All right, 10 minus 13, negative 3. Negative 6 plus 8, 2. 0 there. Negative 15 minus 3, negative 18. And 9 plus 1, 10. All right, I'm noticing that I can make this 9 and 5. But notice this is not a multiple of the one above it this time. If I take negative 3 R2 and add that to R3, putting it back into R3, let's see what happens when we do that. Let me give me a little more room here. Okay, so I'm going to end up getting 1, 5, negative 3, 0, negative 3, 2, 0. This zeroes out. Negative 6 plus 5, negative 1. Ooh, I have an inconsistent system. And remember, it's only a linear combination if we can find a solution, right? We talked about that in that definition of linear combination. Therefore, B is not in that plane. The span still exists, okay? There's still a linear combination that we can find of A1 and A2. It's just B isn't on that plane of that linear combination.